Alright, so let's go into network addressing. So I've talked a little about these little points as I've been going through the individual devices, but we'll just go through the sort of layers, kind of. So on the physical layer, we have MAC addresses. As I said before, they are pretty much written onto a chip, onto the network interface card. They can't be changed. It's hardware, not software. The physical layer does not identify the owner, location, etc. As I said before, it's essentially finding a direction and it's throwing it in that direction. It doesn't care who it's reaching, it just knows that it kind of goes in that direction. Another thing I did not cover earlier, I don't think, is the MAC address uniquely identifies the device. No matter what it is, if your device is network capable, it has a unique MAC address that's completely different from any other device on the planet. And it's not going to change for the most part. There are ways to trick it into thinking it's changed, but it's not going to, really. Going from that, we hit the network layer. Layer 3, this is where the router is. It's got the logical addressing. It's the software. It's going to determine the exact position it needs to go. And these addresses, unlike the physical layer, which is set at the factory, these addresses are assigned through software, and they can be variable. That being said, we get into IP addresses. IP addresses, which most people are familiar with these days, I'd say, you know, your local network might be something like 197.168.1.0, something like that, you know. Most people are familiar with IP addresses these days. They're 32-bit, meaning there are 32 bits, bits being ones and zeros. There are 4 octets in each IP address, 4 sets of 8 bits, 8, 16, 24, 32. Then there you have 32-bit. They're written out in dotted decimal notation. As I said, you might have something like 198.162.1.0, something along those lines. That's the dotted decimal notation. This is a set of bits, that's a set of bits, that's a set of bits, and that's a set of bits. And we're not going to get into binary right now, that'll come at a later time, but that's what it looks like. There are 3 classes of IP addresses, A, B, and C. Well, before we get into that, I might want to say there are different ways to arrange these bits. You have the network bits and the host bits. The network is responsible for determining what network you're on, and the host determines the specific device for the most part. It's like living in an apartment complex. Say you live in an apartment complex at 320 Brady Street, but each apartment in that complex has a number assigned to it. So you might be 320 Brady Street, apartment 1, apartment 2, apartment 20, 50, stuff like that. So that's how IP addresses work. Your home address is most likely a type C. So these first 3 octets are going to be your network. Okay, and that leaves this for a device. Now, these 3 classes, A, B, and C, determine how many octets are being used. The network device addressing, it has an inverse relationship, so the more network addresses there are, the less hosts, or devices. And the more devices, the less hosts. Or, I got that backwards. The more devices, the less network addresses. A type A is the first octet, so a network of type A can only be like say 198.0.0.0. That will become the network, and those will become the hosts. And having these 3 octets for hosts means you can have a lot of devices. In fact, you can have 2 to the 24 minus 2 devices. We do minus 2 because there are 2 addresses that will always be taken up by default. The broadcast address will be used by default, and the network address is all zeros, so you can't use that for devices either. But the equation 2 to the n minus 2, you've got 2 to the number of octets minus 2 devices, and seeing as there are 3 octets, you get 24 devices. However, because we're working with bits and octets, we can only have 255 numbers, so 0 to 255. A type A network can only have 255 different networks, although they can have a lot of devices. Type B is we're just going to follow along this trend. So a type B is 198. Yeah, well, let's just do it right this time. 198.162.0.0. Okay, so now a type B, there's your network, and there are your hosts. And for a type C, I'm just going to label these real quick. For a type C network, it's going to be something along the lines of 198.162, and then that's where you get your 3rd octet. So those 3 octets of bits becomes your network, and the remaining 1 is your host. So now that we've covered IP addressing, and that will come up later as well, so we're just going to stop there. We're going to go on to routers. Routers act as a gateway between networks. You may have guessed, as I mentioned earlier, a router connects 2 different networks. It's also going to determine the data route. So whatever path it's going to take to reach the destination, the router is going to handle that. And then, as we just discussed, it's going to cover IP addressing. Okay, yeah, we're not done with week 5 yet. I thought we might be, but not quite. We're getting there, though. Don't worry. What have we got here? Routing protocols. There are a couple of different ones. I'm not going to go in too much in depth on them, but there's distance vector and link state. Just reading over these notes, the distance vector is old, slow, simple, and has a limited size, and it runs on RIP, which is Routing Information Protocol. A link state, however, is newer, it's fast, it's unlimited size, it's complex, and it uses BGP, or Border Gateway Protocol. I'm not going to elaborate too much on that. We're just going to move on down to servers and TCP ports. So I'm going to zoom in here because my little sketches aren't that big. I'm just going to have to remember to zoom out again. But we have a couple of different things we can do here. If you remember my blog post on the OSI model, it goes 7 to 1. This being, application down, 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 all the way to the physical layer. So what you've got here is the encapsulation path, and this is, on a fundamental level, is exactly what's happening in networks. It starts with the application. You're writing an email. You write your email, you hit send, and it's going to go down the layers, and it's going to get down to the physical layer, and it's hit the router, it's hit everything, it knows where it's going, and then the physical layer, that signal is transmitted across a network to the destination, and then it goes from electrical signals on the physical layer, and then it goes up to a digital binary, and then it goes up and up and up and up back to the application level, and lo and behold, the person you sent the email to received the email. Now there are a couple of different models we can look at here. that being the encapsulation path, and this being the communications path. Now, what I really want to discuss here is you've got a server model and then a peer-to-peer model. So a server model has a client and a server, two different entities. Your server is going to be the host of connection, is going to handle the data, and the client is going to, think of it as a calculator. The client is punching in the numbers, the server is doing the calculations and sending information back. Now, the alternative to this is the peer-to-peer model. Now, if you play video games like I do, you know a lot of games run on the peer-to-peer model, and a lot of people don't like that. It has an issue with lag or latency. Peer-to-peer allows a lot of frustrations with that. So the peer-to-peer, having the client and a server application running on the same device. Games like a fairly recent one being For Honor, that received a lot of flack for being peer-to-peer, used this model. So there's usually a host that hosts the connections, a primary host that is going to run a server, and then every other incoming connection is going to go through that device before being sent back out to the other devices. Zoom back out here to the proper size. A little bit in. Okay. So then we discuss server types. Now, I think the most recognizable server that I think everybody knows are web servers that run on HTTP or I am drawing a blank on this. Hypertext. Well, now I have to Google this. Yeah. It's got to be Hypertext. That's not. That's my website, by the way. It just filled that in for some reason, and I don't know. Let's try that again. I'm not even sure you could even see that, but we're just going to try this again. There we go. Hypertext Transfer Protocol. That's what I was missing, the transfer. Hypertext Transfer Protocol. That's your web servers. Yahoo, Bing, Google. Nope. ESPN, Facebook, Twitter, whatever you may use. All HTTP servers. Now, going along with that, we also have DNS servers. DNS servers are very important. The domain name service. This is, without DNS, you wouldn't be able to type in google.com or facebook.com. You'd have to memorize and type out the IP address every time. And seeing as how we just went over IP addresses, that's not something pretty, So the domain name service is going to allow a name in plain text to be assigned to an IP address. Very important. Another server that probably wouldn't let the internet work if it was absent. That's some pretty bad English. I'll have to revise that. Another server that makes the world turn is an FTP server, or a file transfer protocol. Now, an FTP server allows people to very easily access their web servers remotely and to add files or edit files fairly quickly. Without this, websites would be very difficult to maintain. And I'm just going to flash this on screen, and if you'd like to see this in greater depth, go ahead and pause this now. These are some of the most common ports that routers use, or servers rather. If you'd like to check these out, research them more, here's a good list of them. And that's going to cut it for this vlog.